transformation. Okay. Today, we will start the chapter 2. We have finished up the chapter 1, and you have seen all 4 sections of chapter 1 and preliminaries. You have problems in chapter 1 to solve. So you try to upload your draft of the proofs and solutions on the problems of yours and ask your classmate to check, to finalize it. So work together to get the finalized answer that can be presented here. The numbers and the quality of your finalized problems and your participation in that process will be counted. Okay, Chapter 2, Unitary Equivalence and Normal Matrices. First definition of Chapter 2 is about congruence transformation. Congruence transformation. Okay. Suppose S is a non-singular matrix. Then the map from A to S star AS. A to S star AS. This is a linear transformation on the set of n-dimensional matrices, and also it is called the congruence transformation. Congruence transformation. You have seen this type of similarity transformation before. This is a generalization of this in a complex field. Okay. First fact: this congruence transformation is an equivalence relation. So it satisfies 3 conditions on the equivalence relation. Reflexive, symmetric, and transitive. It satisfies it. First definition, orthonormal set, ON set, orthonormal set. The set of vectors is called an ON set, orthonormal set, if they are orthogonal, they are different, and the lengths of each vectors are 1. Okay, we can just write it down as a Kronecker delta for the inner product of 2 vectors in the set. So we now have orthonormal set. Okay. First theorem. Suppose S is a orthonormal set, then S is a linear independent set. This is orthonormal, then it is linear independent. It's very easy to prove. Let the linear combination of that ON set be 0. And multiply the complex conjugate of the same thing on the left. Then left-hand side should be 0 because that's the inner product of 2 0 vectors. But the right-hand side turned out to be this because it is also normal. So when I is not same as J, or the inner product between those 2 different things are 0. So only the same things are left. Okay? And since this was a complex conjugate, we have alpha I here and alpha I here and Vi here, star, and Vi here. And the summation of this from I equal 1 to K. That's what we have here. But since it is ON set, if I is equal to I, then delta I is equal to 1. So this part will be 1 for all i's. So we only have this. What that means is this scalar alpha i's are all zeros. So from the definition of the linear independency, this vector vi's in the set S are linearly independent set. Okay? Unitary matrix. A matrix is called unitary if the complex conjugate of U times U is an identity matrix. Then we call this matrix U is unitary. Okay. When U is a real matrix, then this turns to be this way, which gave us the definition of real orthogonal matrix. Okay. So this is a generalization of real orthogonal matrix to the complex field. Okay. This is the main theorem for the unitary matrix. This gives the full characterization of the unitary matrix. They are all equivalent. They are all equivalent. If you use unitary, we know the definition is U star AU is equal to identity. Then we can show U star is equal to identity. And if it's unitary, then since because of that, these are those two are two equivalent statements. And from this definition, we know U star is equal to U inverse. And this gives us the columns of U are also normal sets, and also the rows of U are also normal sets. These are the things which were done in elementary linear algebra class. This all comes from the definition directly. So all these parts are easy and clear, and you have seen it before. Only part that you have not seen is this. So if we can show A implies G and G implies A, then we have everything here. First, proof from A to G. It is easy. If U is unitary, then you can think the inner product of UX itself. Then from the definition, you have this UX star here and UX here. That gives us this. But from the definition of the unitary matrix, we have the identity in the middle of X star and X. So we have X star X for any X in Cn. Okay? So we have this. So this is the only part that we need to show to complete the characterization theorem for the unitary matrix. Okay? And this is a standard technique. This is a very standard technique. Okay. With the given condition that this condition holds without this in the middle. So we suppose we have this. That we want to show UXU is equal to identity. Okay. Since this works for all X, we can choose X as some e to the I, or e to the I plus e to the j, and e to the I plus I times e to the j. Okay? This is a very standard technique. Then what we can show is, if we find the inner product of that x, which is EI. EI means this vector, 0 and 1s and all zeros at the i's component. That's the vector EI, standard basis here. If we think that, then we can think since this works, so we can think of this. Okay? We know that's equal to 1. Okay, but this says this is the product of the i's row of this matrix and j's column of this matrix, which says the ith element of this matrix u star u. So we want to show u star u, the ij's element is equal to 1 or 0 if I is equal to j, if I is not equal to j. That's what we want to show. Okay? So from here we showed u star u i's component entry is equal to 1. So next thing is we have to show this u star u ij's components are all zeros, up and down both. So we choose these two arbitrarily chosen vector. So we can, it works for any arbitrarily chosen vector. So we can choose EI and EJs. Okay. Think about it. Think about these two vectors. This is I entry and J entry. Addition of them. They are 2 because each of them are 1. And then we can think that as the inner product of these two vectors. Okay. So from the given condition, we can rewrite it in this way. Okay. Then we can think. We can split it out in this way. What that means is this is 1 and 1 because it's I and I's and J's are here, and these two left here. That's what we have. But these two can be cancelled out, so we know this part is equal to 0. For this special choice, so we can do the same thing with this. All the same, except it has i's here. What that means is, here we have the addition of these two elements is equal to 0, and here subtraction of those two elements are zeros. That's what we have. If we combine these two, we can have all u star u ij is equal to 0 for ij that are distinct. Okay, so we have here for all like this. But that means this matrix is identity. That's the definition of unitary matrix. That's the part A is done. The important thing of here is whenever we have a condition that works for arbitrary vector x, this is one technique that we choose the element that we can use. Okay? So now we have this equivalent conditions. So now we can use any one of these whenever we need, whenever we solve any problem in the textbook and any others in our papers. Next, we think the n by n unitary group. Let's this U is a set of n by n unitary matrices. This is a subgroup of generalized linear group of the size n by n. Okay. Because the here it has more than that actually. There is a note after this 2.17 which says if we think Mn as the vector space of the dimension n square, then that can be considered as the Euclidean space, metric space. If we think the usual norm, think L2 norm, and we can define the matrix 2 norm in this way, like what we did for the vector. Since that can be considered as a Cn squared vector space, so definitely we can define the L2 norm for that. Okay, so now we define a very simple matrix norm induced from the vector norm. Then we can use all the concept that we have used in the matrix space. So we have a definition of closedness and boundedness. If we use those concepts, then we can think the set of unitary matrix as the compact subspace of the vector space Mn. Because we can show this subspace is bounded and is closed by using the matrix 2 norm that we just defined from the vector norm. For any matrix, any unitary matrix in that group is bounded with the L2 norm, and also the set of all unitary matrices are closed. We can show it by showing that every sequence in U has its limit in U. Suppose this series of the unitary matrices in U that converge to a unitary matrix pointwise. Suppose we have Uij of this I's matrix, then it converges each of these components. Suppose the sequence from I to infinity, then this converges to the matrix U like this. Pointwise, it's just like a vector. Okay, so if we define, if we use this definition, then for each I is satisfy this condition, that means each of the component of the matrix converges U to U, Ui star to U star, Ui to Ui to U. Okay, so what that means is pointwise, by the pointwise convergence, you have this condition. That means U star U, the limit is equal to identity, that means the limit is also a unitary matrix which is in U. So it's sequentially closed. If U is sequentially compact, then in a matrix space it's always compact. So you can have this fact. So now we have the set of unitary matrices, not only as a group, also the subspace, the vector space. It is also compact subspace of the vector space Mn of dimension and square. Okay. Okay, next. Okay. This is just a generalization of the concept. Suppose A star, if A inverse is similar to A star, if A inverse is similar to A star, then there exists a non-singular matrix that A is equal to B inverse B star. That means A can be factorized with detailed proof of this matrix. So you can read it. Okay, and there are some problems, homework problems in page 71. You may try. These are very important. Also can be used widely, so you better try 1, 2, 3, 4, 5, 6, 9, 10, and 12. You may choose by yourself. So you can do it by yourself. You can initiate it. Okay, next definition. A and B are unitarily equivalent. Unitary equivalence. If there exists a unitary matrix U such that U star A U is equal to B. Unitary equivalence. That's the definition of it. So, unitary equivalence. This is a theorem concern on that definition. Suppose there exists a unitary matrix U such that U star A U is equal to B, then 2 norm of the matrix A is same as 2 norm of the matrix B. Okay, yeah. We can observe the 2 norm that we defined. The summation of the square of every entries in that matrix. That can be considered as a trace of A star A. Isn't it? Because Aij conjugate Aij is like this. Summation. That's all the terms and square terms. Okay. So we know the square of 2 norm of B can be considered in this way, and B is same as U star AU. Can rewrite it in this way, but this U matrix is the unitary matrix that can be considered in that way. We know when you multiply the unitary matrix on any side, it doesn't change the trace of it, because it is a similar, unitarily similar. So this is same as this, which is the square of the 2 norm of A. So those big theorems give us a very important fact that we can really use. Next, the rotation. You have seen this matrix. If you multiply this matrix on I slow and J slow, Suppose we have the matrix is a matrix, and here cosine theta and sine theta here, minus sine theta here, cosine theta here, I is low, and I is column, and J is column like that. All the others are here the ones, and the main diagonals are ones, and all others are zeros except those four. Then what that means is it rotates any vector of the two axes, I and J axes. It's I's axis and J's axis. It rotates with the angle of theta degrees. Okay. If we use it properly, then we can do 3D computer graphics with it, and all others, not only on three-dimensional spaces, but also for n-dimensional vector spaces. And on other things, another example. These are the example of the unitary matrices. These are all the examples of unitary matrix. And another good example of unitary matrix is household transformation. UW. This UW is called the household transformation. This is the linear transformation. This is made with only vector, isn't it? If you have a vector, then from the vector you make a matrix. You multiply the scalar here and subtract it from the identity matrix. Now you have a matrix, which is a linear transformation, n by n matrix. This matrix is a unitary matrix, and also it's a Hermitian matrix. I gave this problem to some of my undergraduate students before. Yeah, here's the proof, and this is more well written. Yeah, when you have this matrix, and this matrix is real sum. And the previous one is just a general version of this proof. As you see here, if you multiply these two matrices, then you can see it can be simplified in this way. And eventually, these two are cancelled, and only the identity matrix is left. What that means is this matrix is real sum. If you change it to the complex matrix, then you have a complex version of that proof of the household transformation. This is just a little bit general form of it. Okay? Yeah. I have given that problem a couple of times for the freshman linear algebra class. The next, Schur's theorem. Schur's theorem. Yeah. This is one of the most important theorems because it works for every arbitrarily chosen matrix. Whenever you have any matrix, you can simplify to an upper triangular matrix, then you can start from there. This theorem says, suppose you have an n by n matrix A, and you have n eigenvalues in some order, counting multiplicity. Then there exists a unitary matrix U such that U star AU is equal to an upper triangular matrix with all diagonal entries, eigenvalues, in the order that we can choose. Okay? Proof. Here. This is Schur's theorem. Here's the proof. You must have seen it from the elementary linear algebra class. Okay. We use the mass induction. When the size of the matrix is equal to 1, nothing to prove. The diagonal entry is an eigenvalue, and it is an upper triangular matrix. And order is there. Suppose it works for any matrix of size n-1 by n-1. Then we show it for the n by n matrix. Let lambda 1 is the first eigenvalue that you choose. Then there is a corresponding eigenvector that we normalize it and say it is x1. Then by the basis extension that we covered in the preliminary chapter 0, there is a ON basis of Cn, including x1, which was the eigenvector of A corresponding to the eigenvalue lambda 1. Okay? Since they are also on our ON basis, we can make a matrix U0 with those ON bases as columns. Then from the characterization theorem for the unitary matrix, we know that matrix U0 is a unitary matrix. This is U0 is a unitary matrix. Okay? And also, we know AX1 is equal to lambda 1 x1. So the first column of A U0 is lambda 1 x1. So the shape of this matrix, U0 star A U0, how it looks like. This one was lambda 1 and all zeros here, and something here, and here is another matrix, submatrix. Okay, this theorem shows it. This is the shape of the matrix that we have. This A1 is a submatrix of A. So n by n, size of n by n minus 1 by n minus 1. And one other important thing is the eigenvalues, the characteristic polynomial of this matrix can be written in this way. So the very important thing is the eigenvalues of A1, what are they? The root of these two characteristic polynomials are same. So here we have all lambda 1 to lambda n there. Here we have lambda 1 here. The last of them should have all others. This is very important fact. Not many books mentioned it clearly. Okay, this is clearly lambda 2 to lambda n. With this, we can use the mass induction hypothesis. There exists another unitary matrix U1 hat that makes this is similar to A1, the submatrix A1 is similar to upper triangular matrix with all these eigenvalues as a diagonal in the order that we like to have. Okay? Then this unitary matrix has a size n minus 1 by n minus 1. So we define another matrix U1 like this, having U1 hat as a submatrix of U1. Then we can think U not U1 star times A times U not U1, which is this, which makes all works in this way. So now you have upper triangular matrix T, as we like to have all the eigenvalues on the main diagonals. And also, this matrix is a product of unitary matrix. Since the set of unitary matrix is a group under the matrix multiplication, so the product of two unitary matrices is also a unitary matrix. So it satisfies all the required conditions for the sure theorem. Now we have sure theorem. That's it. That's the proof. Okay. Here, last note. Every arbitrary matrix, every matrix is not always unitarily diagonalizable, but this sure theorem gives us at least upper triangular matrix, which is unitarily similar to the given any matrix. But by using this sure theorem, we can show every Hermitian matrix is unitarily diagonalizable. That's another byproduct of this important theorem. Okay. Yeah, we can review what we have learned today. Yeah, when A is an entire matrix and AI is a submatrix, then this equality on the derivative of the characteristic polynomial works, and we define the eigenspace, and we define algebraic multiplicity and geometric multiplicity. We found the relationship between these two, and we defined the left eigenvector, which is going to be very important. This gives us the bi-orthogonality between left eigenvector and right eigenvector for the distinct eigenvalues. And we had a definition of unitary matrix, and we have a characterization of unitary matrices, and also connection to the functional analysis, and also we have seen some examples of unitary transformation, such as rotation and Hausfelder transformation, and we proved the sure theorem. There are some more, but yeah, since the time's up, I will quit there. I will continue the last of it later. Okay. Any questions so far? Any questions?